Hey everyone, and welcome to this explainer. At the absolute heart of thermodynamics, bond formation, and structural stability, there's one relentless little driver running the show, the electron. For those of us who study chemistry, we know that every single reaction is, at its core, an energetic transaction. So today, we're going to put on our molecular accountant hats. We're going to track these continuous transactions and examine the really strict ledgers and hidden mechanisms that govern how electrons are bought, sold, and traded in this invisible, dynamic marketplace of redox chemistry. Here is a quick look at our agenda for today. We'll start with exactly what a redox reaction is, then move into tracking electrons using oxidation numbers. After that, we'll expose the fractional oxidation illusion, categorize the different types of redox reactions, and wrap up with the really fascinating disproportionation phenomenon. All right, let's dive right into section 1. What is a redox reaction? When we're looking at a complex chemical equation, it's honestly incredibly easy to just focus on the macroscopic changes, right? Bonds are breaking, new bonds are forming, molecular architectures are completely rearranging themselves. But down at the fundamental, subatomic level, the law of conservation of mass and charge strictly dictates that in every single one of those reactions, the electrons have to be precisely accounted for. Seriously, where do they actually go? They don't just magically vanish into the ether, and they definitely don't spontaneously manifest out of nowhere. If electron density shifts away from one atom, it fundamentally absolutely must be gained by another within that closed system. The answer to that mystery lies in the constant give and take between two inextricably linked processes. On one side of our chemical ledger, we've got oxidation. At its very core, oxidation is the explicit process of losing electrons. Now, classically, chemists also define this as adding oxygen or removing hydrogen. And then on the flip side, we have reduction. This is the exact opposite, gaining electrons or adding hydrogen and removing oxygen. Think about a highly recognizable redox pair, like sodium metal reacting with chlorine gas to make everyday table salt. The sodium atom completely surrenders an electron. That's oxidation. Meanwhile, the highly electronegative chlorine atom eagerly scoops that electron right up. That's reduction. It's a perfect atomic seesaw. You literally cannot have oxidation without a corresponding reduction happening somewhere else in the system. Now, this brings us to a naming convention that historically trips up almost everyone when they first encounter inorganic chemistry. Meet the oxidizing agent or the oxidant. By definition, this is a substance that supplies oxygen or electronegative elements, effectively stripping electrons away from another molecule. But here's the totally counterintuitive twist. To force oxidation onto that other substance, the agent has to aggressively take those electrons for itself. And by taking on that extra negative charge, the oxidizing agent itself actually undergoes reduction. It acts as the aggressive buyer in our atomic marketplace, constantly pulling electron density toward its own nucleus. Conversely, we have the reducing agent, or reductant. This is a substance that supplies hydrogen, or highly electropositive elements. So the crucial takeaway here is that reducing agents actively sacrifice their own valence electrons to force reduction onto another substance. Because they are happily giving away their own negative charge, the reducing agent itself undergoes oxidation. It's essentially the ultimate chemical philanthropist, willingly donating its electronic wealth to drive the reaction forward. Okay, let's move on to section 2, tracking electrons with oxidation numbers. Just as financial accountants rely on standardized rules to balance complex corporate books, chemists use very strict ledger laws to assign precise oxidation states. Let's walk through these. Elements just hanging out in their uncombined free elemental state, like diatomic oxygen gas or a solid block of pure iron, they get a baseline oxidation number of 0. Easy enough. Alkali metals with their single reactive valence electron are strictly assigned a +1. Oxygen is highly electronegative and almost always takes a -2, unless it's in a rare exception like hydrogen peroxide, where it acts as a -1. Hydrogen typically acts as a +1 when bonded to nonmetals. And the ultimate balancing rule for all of this, the algebraic sum of all oxidation numbers in a neutral compound must perfectly equal 0. Take a simple water molecule. 2 hydrogen atoms at +1 each, combined with 1 oxygen atom at -2, perfectly nets out to 0. It's an airtight accounting system. But we do need to make a really critical distinction here between valency and the oxidation number, because they're not the same thing. Valency is simply the physical combining capacity of an element. It's essentially a hard count of how many covalent or ionic bonds it can form. Because it's a discrete physical count of structural bonds, valency is always a whole number, and it inherently lacks a positive or negative sign. The oxidation number, on the other hand, is a mathematical assignment of residual charge based on atomic electronegativity. It can be positive, it can be negative, it can be perfectly zero, and strangely enough, under certain strict conditions, it can actually even be a fraction. Which perfectly tees up Section 3, the fractional oxidation illusion. I want you to really think about this number for a second. 8/3. If you meticulously apply those standard ledger laws we just talked about to calculate the oxidation state of iron in the magnetic oxide compound Fe3O4, the basic algebra spits out an oxidation state of plus 8/3. Let that sink in. An electron is a fundamental elementary physical particle. You cannot split a discrete electron into fractions. An atom can't surrender exactly 33% of a localized particle. So how on earth does a stable molecular compound end up with an 8/3 charge in our official accounting books? The incredible reveal here is that the fraction is an absolute mathematical illusion. It's just an artifact of averaging. Let's look at the actual atomic structures of a couple other compounds to prove it. Take tribromo oxide, Br3O8, and the tetrathionate ion, S4O6, with a 2- charge. If we look closely at the individual atoms in the bromine compound, the 2 terminal bromine atoms on the ends are bonded to 3 oxygen atoms each. Those oxygens aggressively pull away electron density, putting those terminal bromines at a +6 oxidation state. But the bromine atom sitting right in the middle is only bonded to 2 oxygens, leaving it at a +4 state. If you average them, 6 + 6 + 4 divided by the 3 total bromine atoms, you get exactly 16/3. The exact same mathematical trick happens in that sulfur compound. The outer sulfur atoms sit at +5, while the inner sulfur atoms bonded only to themselves are at absolute 0. 5 + 5 + 0 + 0 divided by 4 equals 2.5. So a fractional oxidation number is merely a statistical average of different, distinct integer states residing within the exact same molecule. The math is really just summarizing a much more complex structural reality. All right, let's zoom out a bit for Section 4, categorizing redox reactions. We can broadly group these redox mechanisms into a few primary types, and they function a lot like chemical corporate mergers and breakups. First, we have combination reactions. This is where simple element A and element B merge to form a more complex compound, C, like solid carbon reacting with oxygen gas to make carbon dioxide. Second is decomposition. This is the breakup, where a larger parent molecule physically splits apart into smaller elemental components. Think liquid water breaking down into hydrogen and oxygen gas when exposed to an electric current. And third is displacement. This is effectively a hostile takeover, where an atom or ion already inside a compound is forcibly replaced by a completely different, much more aggressive element. For example, dropping solid zinc into a copper sulfate solution will forcibly kick the solid copper entirely out of the solution to form zinc sulfate. But what dictates who gets to displace whom in these hostile takeovers? It all comes down to intrinsic thermodynamic properties and a strict hierarchy of metals. Basically, reactivity perfectly dictates displacement. Zinc, for instance, is highly reactive compared to copper, and copper is more reactive than silver. The core reason for this lies in their standard reduction potentials. Zinc has a much stronger innate tendency to release its valence electrons than copper does. Because of this, stronger reducing agents literally force their electrons onto the weaker ones. Zinc happily dumps its electrons and bullies copper out of an ionic compound to take its place. But copper simply lacks the energetic strength to do the same to zinc. In this molecular marketplace, it is absolutely survival of the most reactive. Which brings us to our final topic, Section 5, the disproportionation phenomenon. This is where things get genuinely wild. Think about the decomposition of a super common household compound, hydrogen peroxide, H2O2. As the peroxide molecule decomposes into liquid water and oxygen gas, something amazing happens with the oxygen atoms. Based on our ledger rules, the oxygen starts at an unusual -1 oxidation state. As it reacts, some of that oxygen successfully reduces down into a more stable -2 state within the water molecule. But at the exact same time, the rest of the oxygen oxidizes up to an elemental 0 state to form the oxygen gas. A single chemical element is acting as both the buyer and the seller of electrons simultaneously within the exact same reaction mixture. It is literally transacting with itself. And hydrogen peroxide is definitely not the only rule breaker here. Several distinct nonmetals pull off this bizarre simultaneous give and take under the right conditions. Phosphorus can disproportionate to concurrently become phosphane and hypophosphite. Elemental sulfur can split its structural identity into both thiosulfate and sulfide. Even diatomic chlorine gas, if you drop it into an alkaline medium, will simultaneously undergo oxidation to form hypochlorite and a reduction to form a standard chloride ion. It just needs that specific alkaline trigger to force this remarkable dual pathway. Which leaves us with a pretty profound thought to wrap up this explainer. If a single chemical element possesses the thermodynamic capability to both steal and surrender fundamental electrons at the exact same moment, perfectly playing both sides of the ultimate energetic transaction, what other hidden dualities and structural paradoxes exist in the physical world around us? It's a wild thought. Keep tracking those invisible atomic transactions because, as we've clearly seen today, the most fascinating scientific stories are always hiding right there in the ledger. Thanks for joining me.